All right, howdy everyone. We're on section 3.6, consistency. Let's think about contradictions. Here's a logically impossible sentence, P and not P, and is a conjunction. And as a conjunction is saying that P is in fact the case and not P is in fact the case. For example, from page 138 of the textbook, Tom is taller than Bill and Tom is not taller than Bill. Now, we don't need to know anything about Tom or Bill to know it is logically impossible. I mean, after all, it is the form of P and not P. Indeed, if Tom is taller than Bill, that logically cancels out the possibility that Tom is not taller than Bill. And likewise, if it is true that Tom is not taller than Bill, it cannot be that Tom is taller than Bill. Two truth diagrams can illustrate that a logical contradiction must be false. That is, whatever the truth value of P, the molecular sentence will be false. So on the one hand, it may be that P is true, and then we can look at the molecular sentence P and not P and do a truth diagram. So P is true, and we have a negation here, so this turns into something that's false. And then if we look at this conjunction, we have true and false, so this is a false statement. And P can also have the value of being false, on the other hand. So let's look at the conjunction P and not P. So P is false. We have this negation here, so this turns into something that's true. And we have the values false and true. So the molecular sentence, the conjunction, is false. So there's no possibility that this sentence can be true. That is, it's logically false. The conjunction P and not P is an immediately obvious logical impossibility or contradiction. But you may have much more complicated molecular sentences, and it's not so obvious that it is contradictory, but it may in fact be contradictory. So what do you do then? Then you would go through various logical inferences and equivalencies to derive a logically impossible sentence akin to P and not P. That is, if you can derive validly from that sentence something akin to that form, the conjunction P and not P, then that sentence that you started with must be logically impossible. It must be a contradictive statement. Moreover, you may have a set of premises. You have multiple sentences, and it may turn out that each individual premise, when analyzed all alone, isn't contradictive. Nevertheless, together that set of premises does entail, by logical inference, by a valid argument, a contradiction. In such a case, the set of premises would then be inconsistent. So an inconsistent set of sentences, you have two or more sentences that have no possibility to be logically true together. And such an inconsistent set of sentences entails a contradiction in the system. That is, you can logically derive validly a contradiction of the form, the conjunction P and not P. Let's think about these two examples. Here I just have a single premise, but the same process is at play if you have multiple sentences as premises. So if you look at the first one, not, parentheses, not S or S, close parentheses, the negations there makes things a little confusing. So it's not immediately apparent it is a contradiction, but we do have De Morgan's law, so let's just apply that. So for our second sentence, and this will be our first sentence, our premise, we can get not S and not S by De Morgan for sentence 1, and because of double negation, we have that not, that's the same thing as a positive statement, so to speak, so S and not S. And here we have our contradiction. In this case, we can say that this sentence here and this sentence here are really logically equivalent or identical. So it truly is a contradictive sentence. In the second premise, we have this big conjunction. So It's not obvious right away that this is a contradictive, logically impossible sentence, but we can show that. So because it is a conjunction, let's engage in some simplification. So for 2, we can say if S, then R, with the simplification of 1. And likewise, we can say not parentheses, not S, or R, close parentheses, but the simplification of 1. For 4, we can engage in De Morgan on sentence 3, so we can get not S and not R. And like before, we'll do double negation, so we can get S and not R. And if you notice, we have this S here, and S appears here in this conditional, so we could eventually get R by modus ponens, and then we would have R contradicting this not R. So we would we would then get a contradiction. So for 6, we'll get S by the simplification of 5. For 7, we can get R by modus ponens with 2 and 6. With 8, we can get not R by the simplification of 5. For 9, we can get R and not R by this conjunction law with sentences 7 and 8. And here we have our contradiction. So because the sentence we started with does imply this sentence here, it's not logically equivalent to it, but nevertheless does entail it, we know that the sentence that we started with is logically impossible. Using our mind's eye, we'll treat exercise 9 just as a warm-up. We want to know which of these 3 propositions are logically impossible, i.e. logically contradictive. If you look at proposition 1, we're told that this is Thursday or this is not Thursday. Would this be a logically contradictive proposition? It is a disjunction, and we know that in disjunction, only at least one of its disjuncts or choices has to be true. It doesn't follow that both have to be true. So it's perfectly good as a sentence that's not logically contradictive. On the other hand, obviously, if we had a conjunction, if we said this is Thursday and this is not Thursday, we would have something that's logically contradictive. By the way, this brings to mind a very interesting issue called the law of excluded middle or the law of bivalence. It's actually a little bit more tricky than people realize for a variety of reasons. I think because people don't see that the law of excluded middle doesn't deny, so to speak, a spectrum between things, because the law of excluded middle only applies to truly contradictive propositions. So if I say T versus not T, these are truly contradictive propositions. Okay, so it's not denying spectrums. It's not saying that, for example, everyone is either beautiful or ugly. But this is not an application of this excluded middle, because there are degrees. People can be in between being beautiful and ugly, right? So the law of excluded middle only applies to these clear-cut contradictory judgments. But anyways, there's also some people say, well, don't you have an intermediate position sometimes where we don't know if something is true or something is false? Okay, you can have logic systems developed where the law of excluded middle doesn't hold, but with propositional logic, we do assume the law of excluded middle. But anyways, that's a little bit of a tangent. In number 2, we're given the proposition, if Jane is tall, then her brother is not short, but Jane is tall and her brother is short. It's a very long sentence, and it's a little bit confusing in how we should interpret this, but I think we should notice that, let me just actually erase that. We have this comma here, so I think what we have is a conjunction overall. So this but is really treated as if it is an and. We can do that in everyday speak. So here we have this conditional, this if then, and this is combined with this conjunction. So if we wrote that out in symbolic notation, we'd have something like, in parentheses, if J then not B, close parentheses, and parentheses, J and B, close parentheses. And here we can see there's a contradiction because we have this B and this not B. So we know J is a case, so we could affirm the antecedent. We could then affirm the consequent, but we have not B versus B, and those are contradictory propositions. So we violated the law of contradiction. So sentence 2 is logically impossible. Number 3 we have, it is not the case that either Jim won his match or Jim did not win his match. This is actually kind of like number 1, right? It's just that we start out with denying this disjunction, right? So we have either Jim won or Jim did not win. But we're saying this is not the case. So this is contradictory because, in effect, we're actually denying the law of excluded middle here, by the way, right? Because we're saying that with two contradictory judgments, one doesn't have to be the case. So that's really what's violating the law of contradiction here. If it's not clear, we can just use De Morgan. So we have this not parentheses J or not J, close parentheses. Well, this would be equivalent to, let's see, not J and not J, but that would be equivalent to not J and J. So it is indeed a contradiction. Actually, before we do exercise 10a, I want to talk a little bit more about the law of excluded middle. I don't think I defined it precisely enough, so I better do that before we move on. So we have P or not P. Let's think about this. So the law of excluded middle tells us of two contradictory propositions, one and only one must be true. And the key word here is contradictory. Contradictory propositions. For example, P versus non-P. I gave the example of either you're beautiful or ugly. This would be a misapplication of the law of excluded middle because what's contradictory to beautiful is simply non-beautiful. It does not imply ugly. If I said you're not beautiful, does that mean you're necessarily ugly? Maybe it just means you're average. And being average, I wouldn't say means you're ugly, because there's a spectrum. So the law of excluded middle does not deny spectrums. The law of excluded middle only deals with contradictory propositions. So while being beautiful and being ugly are opposite extremes, they're not contradictory. Contradictory does not mean contrary. And likewise, we have to apply the law of excluded middle in a way that makes sense to the content at hand. For example, if I said circles are either evil or non-evil, it has to be one or the other because, after all, we have the law of excluded middle. But that doesn't even make any sense, because how can a circle be evil or non-evil? A circle is not a person. It doesn't have a free will to choose between doing good and bad. So that doesn't even make any sense. So it's really misapplying the law of excluded middle. So again, of two contradictory propositions, one must be true, but the propositions must be contradictory. Okay, so let's look at our three problems here, and let me just erase this. If we look at number 1, we have 4 premises. It's not clear right away if they're inconsistent. We're told they're inconsistent, so they must be. So I think the best thing to do is just to work on number 3, premise 3, and just use De Morgan. So for our 5th sentence, we can get not P and not Q by De Morgan. from sentence 3, notice that not P shows up here, so we can get not S eventually by modus ponens. But for 6, let's first say not P from the simplification of sentence 5. And then we can say not S because we have a modus ponens inference from sentences 4 and 6. And also, S appears here in this disjunction. We're denying it, so we can then affirm not R. So for 8, we can say not R. We have a disjunctive syllogism with 2 and 7. And let's see, not R is contradictory to this R here in this conditional. We're denying the consequent, we thereby deny the antecedent. So for 9, we can say not Q by modus tollens with 1 and 8. 10, we can say Q by double negation of sentence 9. Notice, well, we have this not Q here, and we have Q, so we have a contradiction. So for 11, we'll say not Q by the simplification of 5. And for 12, we'll say Q and not Q, because we have a conjunction law with sentences 10 and 11. And Q and not Q shows we can get a contradiction out of our premises, so those premises are inconsistent with each other. Number 2, we also have 4 premises. But here, it looks like we can figure out what's going on to see why this is definitely an inconsistent set. So if we look, we have T. We can get T out of that conjunction, so we're going to then get P. And we can get this antecedent eventually to get Q. Q can get us not R, but not R and R are contradictory, so we have an inconsistent set. So let's write all that out step by step. So for 5, we can get T by the simplification of 2. Then we can get P by modus ponens with 1 and 5. For 7, well, we want P or S. So let's say P or S, which we can do by the law of addition from 6. We know P is true, so P or S must be true, regardless if S is true or false. So for 8, we can now get Q by modus ponens with 4 and 7. 9, get not R, because now we can have a modus ponens situation again with 3 and 8. For 10, get R by the simplification of sentence 2. For 11, we can get not R and R by the conjunction law with sentences 9 and 10. And now we have a contradiction. They cannot both be true. Not R and R. So if the conjunction is false, we have an inconsistent set of premises. Once again, if we look at our 4 set of premises, it looks like we have a contradiction if we notice that. So we have S, and that's contradictive to not S, so we can get R. Then we can get eventually a Q. But we also know T, so this contradicts not T, so we can get not Q. So really we have a contradiction of Q and not Q at the end of our various inferences, valid inferences. So for 5, let's say S by the simplification of 4. For 6, we can say not S by our double negation of 5. For 7, we can get R, because we have a disjunctive syllogism with 2 and 6. For 8, we can now get R and Q, because we have modus ponens with 1 and 7. For 9, we can get T by the simplification of 4. For 10, we can say not t by double negation of 9. For 11, we can then say not q is the case because we have a disjunctive syllogism with 3 and 10. For 12, we can get q from the simplification of 8. For 13, we can get not q and q by the conjunction of 11 and 12, and there we have, of course, our contradiction. So we have an inconsistent set of premises. This is an important note. Just because you cannot derive a contradiction from a set of premises doesn't necessarily mean that the set is consistent. And we want to be able to show a given set of premises is consistent or that it is inconsistent. The method of truth assignment is a definitive technique to do just this. On the one hand, a consistent set of premises has it that it is possible to assign truth values to its atomic sentences such that all premises are true. That is, all the premises are logically compatible with each other, and therefore you cannot validly derive any contradictions out of that set of premises. But on the other hand, an inconsistent set of premises has it that they cannot all be true. That is, they're not logically compatible with each other. You can then get contradictions out of those premises. So if you can show there's no way in the world that you can get all those premises to be true, you have a bad set of premises. There's no question. So it's a garbage set of premises, and you can get garbage conclusions from that garbage set. Let's work on two problems with exercise 11a. We're to prove the following sets of premises are consistent by showing interpretations in which all premises are true. Number 5, we have 3 premises. First, I'll write a true-false table. So some atomic sentences we will assign the value of being true, perhaps, and some atomic sentences we will assign with the value perhaps being false. We have the premise if R then Q. We have the premise if P then Q. And we have the premise if Q then not T. Here we actually have some wiggle room in terms of our assignments. We could assign some atomic sentences as having either the value of true or false without making any of the premises false. Look at the first premise. We have if R then Q. Well, we might as well assign both R and Q as being true. So we have a true antecedent, a true consequent. So we have a true conditional, and thereby a true premise. The second premise, we have if P then Q. We've already said Q is true. Here the antecedent could either be true or false. So, hey, why not just say P is false? We don't have to, but we will still make sure the premise is true, because a false antecedent and a true consequent has it that the conditional is true. And the third premise, we've already said Q is true. Here we are restricted in what we can do. So we have if Q then not T. We have a true antecedent, so the consequent must be true in order for that conditional to be true. So T must be false. So T is false, but it's negated, so that turns into something that's true. True antecedent, true consequent, so true conditional. And so we have true premise, true premise, true premise. So these 3 premises are indeed consistent with each other. Number 3, 3 premises. I'll create the true-false table. So we have some atomic sentences. We will assign perhaps the value of being true, and some perhaps we'll assign with the value of being false. I like to spell out true and false, because after all we have this atomic sentence that's T, so to abbreviate true as T will confuse me. So might as well spell out true and false. Anyways, we have the premise if T then R. We have the premise if not R then S, and the disjunction, the premise S or T. Again, I think we have some wiggle room here in terms of what we could assign. The first premise, if T then R, we can say both atomic sentences are true, so and that will seems to be consistent with the other two premises. So we'll just say T is true, R is true. So we have true, true, true antecedent, true consequent, true conditional, so true premise. The second premise we have if not R then S. R we've already said is true. That's being negated, so it's false. S can be true or false. I'll just say S is false. So we have false antecedent, false consequent, but the conditional is true. And then the third premise, S we've already said is false, but T we've already said is true. And in disjunction, only one of the disjuncts has to be true, so it's a true disjunction. True premise, true premise, true premise. So these are consistent with each other. For exercise 11b, we'll just do 4 problems. For each of the following sets of premises, tell whether they are consistent or inconsistent. Prove your answer. Okay. So if Mary is oldest, then Jerry is younger than Sue. Mary is oldest, and Elizabeth is not older than Sue. It is not the case that either Sue is oldest or that Elizabeth is older than Sue. Are these consistent or inconsistent? Well, we can notice one thing. So we say in the third premise, it's not the case that either Sue is oldest or that Elizabeth is older than Sue. So Elizabeth is older than Sue, but we're really saying that it's not the case. And we're also saying Sue is oldest is not the case because we have this not. So we're negating that disjunction. So if we're saying Elizabeth is not older than Sue, this is consistent with this conjunction. Elizabeth is not older than Sue. So this does seem to be a consistent set of premises. Let's symbolically write this. So we have, if M, then J, we have M and not E, and we have not parentheses S or E. Okay. So we have a table, true, false. We have the premise, if M, then J, premise M and not E, and the premise not parentheses S or E, close parentheses. If we're going to show that they're consistent, each premise has to be true. The most tricky part is the third premise. So I think we should actually begin there. We have not parentheses S or E, close parentheses. So we're going to want that premise to be true. So we're going to be really forced in the situation to assign both S and E as false. So we'll say S is false and E is false. So false, false. So with this disjunction, so that disjunction is false, but we have to negate it. We have that not, so we turn it into something that's true then. E shows up in the second premise. We've already said E is false. And if it's negated, that's turned into something that's true. And it's a conjunction, so M has to be assigned the value of being true. So true and true is true. So we have a true premise. In the first premise, we have if M then J. M is true. J, we also should assign the value of being true. True antecedent, true consequent, true conditional. So we have true premise, true premise, true premise. So we do have a consistent set of premises. Number 2, A is the winner and C is not third. But if A is the winner, then B is fourth. But if C is not third, then B is not fourth. Is that consistent or inconsistent? It looks inconsistent, doesn't it? We have a conjunction, and we know for a fact that A is the winner, according to the first premise at least. But if A is the winner, then we know that B is fourth. Moreover, we know that C is not third. But if C is not third, then B is not fourth. So the contradiction really is right here. So these are inconsistent premises. We could affirm both consequents because we can affirm both antecedents based on our first premise. Instead of doing that truth assignment, let's just derive a contradiction from that set of premises. So we have for our first premise, we have A and not C. Second premise, we have if A, then B. Third premise, we have if not C, then not B. So for a fourth sentence, we can get A by the simplification of 1. For a fifth sentence, we can get B by modus ponens with 2 and 4. For 6, we can get not C by the simplification of 1. For 7, we can get not B by modus ponens with 3 and 6. And for 8, we can get B and not B with the law of conjunction with sentences 5 and 7. Here we have our contradiction. And so the premises are indeed inconsistent with each other. Number 3, John is in the library, and it is not the case that either Tom is in history class or that Dick is in history class. If Chuck is in chemistry lab, then Dick is in history class. If Ken is in geometry class, then Tom is in history class. If John is in the library, then either Chuck is in chemistry lab or Ken is in geometry class. It's not immediately apparent if these set of premises are consistent or if they're inconsistent. But notice that in the first premise, overall we have a conjunction, and one of its conjuncts is a negation of a disjunction. So really, if you think about it and just apply De Morgan's law, it follows that according to the first premise, it is not the case that Tom is in history class, and it is not the case that Dick is in history class. Now it follows that if Dick is not in history class, then it is not the case that Chuck is in chemistry lab. We have a modus tollens situation. Likewise, if we look at the third premise, if we deny the consequent, we can deny the antecedent. We can deny that Ken is in geometry class. So we're going to deny Chuck is in chemistry lab and that Ken is in geometry class. But we know, at least according to the first premise, that John is in the library. This kicks in the antecedent. The antecedent is the case, so at least one of these two should be the case, but both are contradicted by the above premises. So this is definitely an inconsistent set of premises as a result. Let's write this out in symbolic notation. So our first premise would be what? Be J and not parentheses T or D. The second premise would be if C, then D. The third premise would be if K, then T. Our fourth premise would be if J, then C or K. So these are our premises. And let's derive a contradiction based on those premises. So for our fifth sentence, we could get from the first premise J and parentheses not T and not D because of De Morgan's law. We could then do some simplification of that fifth sentence. So for number 6, we could get not T and not D. For 7, we can just get not T by the simplification of 6. And now we can do a modus tollens inference. So for 8, let's see, we can get not K because of modus tollens with sentences 3 and 7. We do another simplification. For 9, we can get not D from the simplification of 6. And now we can do another modus tollens. So for 10, we can get not C by modus tollens with 2 and 9. For 11, let's get J just by the simplification of 1. And with that J, we can do a modus ponens inference. For 12, we can get C or K by modus ponens with 4 and 11. If you look, we now have a disjunctive syllogism for 13, we can get C because we have a disjunctive syllogism with 8 and 12. We have C, and we also have a not C. So for 14, we can get not C and C by the conjunction law with 10 and 13. And here we have our contradiction. So that means these premises are inconsistent with each other. That's it for this video. Thanks for watching. Up next is section 3.7, indirect proof. It's the last main section for chapter 3. I hope these videos are somewhat helpful, especially with all the many example problems. I'll see you soon. Thanks for watching.